some functions have an inverse. And the way we write an inverse is if we have a function f, then the inverse would be represented by f raised to the negative 1. And that's the inverse. A function will not have an inverse if it's not a bijection. So to test, you want to make sure before you can do the inverse, you need to make sure that it is both. Remember, bijection is both one-to-one and onto. So if a function has the one-to-one property and it has the onto property, then it'll have an inverse. If it's missing either one of those properties, it won't have an inverse. So what is the inverse? Well, the domain and the range swap and in an inverse function, and the mapping is reversed. So let's look at what that looks like. So here we have a function that's defined as a set of ordered pairs. So the inverse of that is f to the negative 1. So I do the negative 1 and I superscript this. So formatting text superscript, and that's how I write the inverse. Now this will be a set of ordered pairs, but the orders will be reversed. So now it will be 13, 4. Right? That's just that reverse. Then it'll be the next one reversed, which is 14, 7. And then the next one reversed, which is 16, 8. So with a set of pairs, all I need to do is simply reverse each pair. And now I've defined the inverse. All right, so that's the inverse just by swapping each individual pair. Now, here's that same function, but it's defined using an arrow diagram. So let's go in and see if we can swap that. So if we go here, here's that function. What does it mean to swap that, right? What it means is that you have to change swap the values on the relationships. So every time there's an arrow, you're going to swap those values. So the 13 comes over here, and the 4 goes here. The 14 comes over here, and the 7 comes here. Now pay attention on this one. They don't swap in order, they swap across the arrow. So the 8 and the 16 are going to swap places because you're reversing the connection, and the arrow identifies the connection. So over here, we're going to have the 16, and over here, we're going to have the 8. So they swap across the connection. And here, we're going to swap the 12 and the 15. So this one becomes 15, and this one becomes 12. So now we've swapped them all. Let's see if we ended up with what we were expecting. So here we have, remember, this is the same one as our pairs. Let's see if we got it. 13 and 4, yep. 14 and 7, yep. 16 and 8, yep. 15 and 12. And so we did that reverse. So this is the inverse. Again, we're going to list this as the inverse. It's no longer the function itself. Now it's the inverse. So I'm going to superscript that, and that becomes the inverse. And that's how you do it with an arrow diagram. Well, now, what about if we have a function that's defined by how you act on it? So here's one that's defined how you act on it. It has a range, it has a domain, that's the domain, and it has a range or a target. It has both the target and a range. And we need to verify that it's a one-to-one and an onto. So we can do that by looking at each one, right? We can substitute. So 2x plus 5 is 2 times 1 plus 5 is 7 when we do that with 1. When we do that with 2, it's 2 times 2 plus 5 is 9. When we do that with 3, 3 times 2 is 6 plus 5 is 11. When we do that with 4, we get 2 times 4 is 8 plus 5 is 13. We do it with 5. 2 times 5 is 10, plus 5 is 15. So what we found is that it's onto, each value in y is mapped to, and it's one-to-one. Each value in x is maps to a different value in y. So it's both onto and 1 to 1. So now we can do an inverse. And for these, the way that we do inverses for them, well, we know that we have to swap the x and y. So that, right, okay, let's get this formatted because this is a superscript. And then we're going to swap the domains. So now it is going to be y mapped to x. All right, so that's how we swap the domain and the target. And now we're going to say where, and we don't really need the where, we can just simply say f of x. So I'm just going to say f of x here on both of them. And to do this, we have to compute it. So we have to say, okay, how do we do this? Well, this is really saying y equals 2x plus 5. So we know what the function is saying. Well, what we want to do is we want to take that now and solve for x, right? The function already tells us that y equals this, right? Every time we put a value for x, we get the y value. So now we want to solve for x. So the first thing I'm going to do is I'm going to swap sides. 2x plus 5 equals y. So I just swap them. And now I want to solve for x. So I can move the 5 over. So I have 2x equals y minus 5. You have to just do your regular algebra. And now to solve for x, I need to divide by 2. So then that becomes y minus 5 divided by 2. All right, so what I did is I took the formula from the function and I solved for x, right? It already tells me y and I solve for x. So now we say the inverse is the function y equal to, and then we use this formula, this formula that we figured out. And that's the inverse. So you swap the domains, you use the formula for y, and you solve for x. And that becomes the end. Should we test it and see if it works? Now we're going from y to x. Right now we're mapping from y to x. So if we take y minus 5, we get 2. We divide it by 2, we get 1. So that's just exactly the opposite. We take, or it's just reversed, right? We take 9 minus 5, that's 4. We divide it by 2, we get 2. We take 11 minus 5, that's 6. We divide it by 2, we get 3. We take 13, subtract 5, that's 8. We divide it by 2, we get 4. We take 15, subtract 5, we get 10. Divide it by 2, and we have 5. So that's how you do it when it's a function that's written in a way that tells us how x acts on y, or how the function acts on x.